Okay, so proving with induction when there are inequalities. Now, here's our question. Prove by induction that 3 to the power of n is greater than 1 plus 2n for all integers of n greater than 1. We still have the same steps. Step 1, we prove for n equals 2. Now think about why I've chosen 2, and it's simply just because the values here that they want me to use, they said it has to be greater than 1. So usually we would test for n equals 1, but we can't here because of this domain they've given us. One thing to do if they give you an inequality in this format is to put it all on one side. So instead, think of it as 3 to the power of n. What do we have? Minus 2n minus 1 is greater than 0. Just makes life a bit easier. So now when we're proving for n equals 2, we know we just sub in 2. So let's have a look what we get, and we say, and I always show this step. I know that you may be able to do it in your head, or you should be able to do it in your head, but show them these lines. Then I'll have, what do I get? 4. And then I'll say which is true. Therefore true for n equals 2. Okay, next step, step 2. Assume true for n equals k. Alright, so we know this step is super easy. All I'm going to do is rewrite the question with k involved instead of n. So I get 3 lots of k minus 2k minus 1 is greater than 0. Alright, there's nothing really I can do from here. A lot of the time we're rearranging, but at the moment there's nothing more I can do at this point, so I'll leave it at that. Step 3. We test for n equals k plus 1, so the next term. So I'm just going to rewrite the question now, subbing in k plus 1. Now generally at this point here, with inequalities, we're just going to look at just focusing on the left hand side. If I clean this up and expand, what do I have? I know that's 3 to the power of k timesing with 3 to the power of 1, because times we plus the indices, and that's what I would get. Expand out this, I get negative 2k minus 2 minus 1 is greater than 0. Let's try and clean things up. I'm going to get 3 to the power of k timesing by 3 minus 2k minus 3. And I don't need that right hand side, do I? Now what happens here with things like your divisibility, we would sub something in and it would come out quite clean. The thing with your inequalities, the piece of information we know and we want to work with is this. We're always working with what we got when we subbed in k. What that means is I need to manipulate that to look like that in some way. So thinking about that, if I can see here that something I don't like the look of is this times by 3. It's not making things look much like this original one, and I want to somehow transform this line here to contain my line for k. That's the whole idea here. If I do that, I can factorize out of 3 out of here. If I factorize out of 3, I'll have 3 lots of 3 to the power of k minus 2k, and I'll come back to that, then minus 1. I know that when I just factorised, I didn't factorise this term out properly, because expanding that I would get negative 6 when it was negative 2k. However, look at the big idea here. The big picture is I got my value of what I wanted in the brackets. But I know that expanding that, I'm not going to get it. Expanding this, I would get 3 times 3k gives me this part here. 3 times negative 2k would give me negative 6k. So, then 3 times negative 1 is going to give me negative 3. So what's going to happen when I expand this out, just on a side note, think here, I'm going to get, and you can put this in your working if you want, but if I expanded that, I'm going to get 3 timesing by 3 to the k minus 6k minus 3. Now that there isn't what I had here. In fact, it is what negative 4k is more. So what you in fact have to do is equal it out and plus 4k. The whole idea is that my aim is to manipulate my line here to contain my line here, and I do that in a way by evening everything out so that it does contain my values with k, but it still also doesn't change what the expansion would be. I hope that makes sense. Now it's as simple as, the hard stuff is done. We know, so since 3 to the power of k minus 2k minus 1 is greater than 0, from step 2, and you can put step 2 if you want, then 3 lots of that is still going to be greater than 0. And I could even just put in one step, 3 lots of that plusing 4 lots of k is still going to be greater than 0. And I know that because I know that k is greater than 0. So I knew that this part here was greater than 0. So timesing it by 3, it's still going to be greater than 0. And plusing 4 lots of k, if k is positive, which we know it is still going to be greater than 0. So I'm done. So therefore, since true for n equals k and n equals k plus 1, hence true by mathematical induction. And I have done. Alright, let's do another one. Let's go with example 2. Prove that n squared minus 11n plus 30 is greater than or equal to 0 for all n greater than or equal to 6. If you want to, pause the video here and give this a go from this point. See how far you can get, if you can do it all, and then check with my solution. Otherwise, the first thing we're going to do is put step 1. It's already in a nice form with all on one side, so I don't have to rearrange like I did last time. So, step 1, we're going to test for n equals 6 because of this idea here. My first value to put in is 6. And when I do that, I'm going to get 6 squared minus 11 lots of 6 plus 30 is greater than or equal to 0, which gives me 36 minus 66 plus 30 is greater than or equal to 0, which gives me 0, which is greater than or equal to 0, therefore true. Well, normally I'll say here, therefore not therefore, which is true. Therefore, true for n equals 6. Easy. Step 2. Step 2, we assume true for k. N equals k. So rewrite the question with k involved. K squared minus 11k plus 30 is greater than or equal to 0. Step 3. Now we're going to test for n equals k plus 1. Alright, rewriting everything with k plus 1 involved. So I'm going to have k plus 1 minus 11 lots of k plus 1 plus 30 is greater than or equal to 0. Now remember, at this point I generally just look at left-hand side. If I do that, let's clean this left-hand side up. Let's expand. If I expand that, I'm going to get k squared plus 2k plus 1 minus 11k minus 11 plus 30. Keep going. 2k minus 11k is negative 9k. Then I'm going to get negative 20. Alright, now remember, this whole idea is that point now where we want to put this value here in here somehow. So what could we do? Let's manipulate it. Well, let's just write the value we want there. We want k squared minus 11k plus 30, because we know that that is greater than 0. But how can we manipulate this line to entail that? Well, I've got negative 11k, so I know to get back to that I'd have to plus 2k's. And I've got 30. I need to get to 20. Now, should that be a positive 30? Yep. So I need to subtract 10. I need to get to negative 20, and I'm at 30. So I'm not going to subtract 10. I'm going to need to subtract 40. Okay, sorry, I've just made a mistake in my notes. Let's go with this then. Just checking I haven't made any mistakes by expanding. And the question was plus 30, wasn't it? Yep. Okay, and then I had negative 2k minus 11k. Then I had 1 minus 10 is negative 10. Oh, sorry. Plus 20. Hopefully, maybe you've been thinking the last 3 minutes. Hurry up and realise. So that was plus 20. And I have plus 30. So I need to subtract 10 to get back to 20. Okay, sorry about that. Alright, so let's have a look now. Now I have what I want here. Okay, I have my value of k. Now, easy, I'm done. Because since k squared minus 11k plus 30 is greater than 0, equal to 0, and we can say so that is greater than 0 since that is greater than 0, and 2k minus 10 is also always going to be greater than or equal to 0 since k is always greater than or equal to 6. Because if you think about 6 being the smallest value of k, that's going to give you 12 minus 10 is 2, which is positive. So it can only get bigger. This number only get bigger, so it's always going to be positive. So therefore, true for n equals k and n equals k plus 1, therefore true by mathematical induction. So that's it. So basically, inequalities, everything is the same. The only thing you need to be good at is adapting what you have to contain what you need it to have. Okay? So adapt what you have when you put in k plus 1 to contain somehow a manipulation of what you had when you subbed in k. And it's always quite nice from there.